So if R is our representative volume, which is let's take 100 by 100, and if you take smaller than the like the importance of R is that if you take smaller than this, if you take any size which is smaller than this, you will have deviation from the property of the material. If you take a given size which is bigger than R, then you will of course get the material properties. So then you call this as R, as representative volume. So why we need to find out R? Because we don't want to take like very large area or volume to compute our properties. We don't want to take that. That increases the computation time, that increases the experimental cost, etc., etc., etc. So we want that size. We can take small margin also, like say R is 100, so I can still take the size of like R is 150. I have taken enough margin so that I don't get any error if there is like unwanted variation in a particular area, in a particular point. So to counter that, I have taken a margin also. So if this is my RVE, if I take this one, I will say with more confidence that this will represent my property. So the aim here is to find out what is that R. So now we will come to this part. So we have run a correlation here. So this is our material. For the time being, we have to do this exercise, we have to assume that this is uniformly loaded. But it is not the case. You know that it is not the case. The stresses at each points are different. The loading condition at each point are different. In such condition, we cannot compute RVE. That does not qualify for the definition of RVE, because the basic assumption, the first assumption is this, that all these points should be uniformly loaded. But in a given space, suppose if I take this space, I'm just drawing a rectangle here. So if I have taken this rectangle, suppose, and in this rectangle, if I say that all the points are uniformly loaded, then also I can find out RVE of this particular loading case. Okay. So how I do is, first I decide that in this space I am going to draw my areas. Now let me draw different areas in it. Okay, this I have drawn R naught as a bigger area, and now I'll draw more areas inside it. This is one. There is no need to be like, they need not to be at different locations. There can be overlap. There is no problem in that, and there has to be overlap. There should be overlap. So I have to draw enough these points. Now I'm randomly taking these size. When you do this exercise, when you do actual calculation, you have to be sure on the size of these areas, and that all the size of these areas should be equal, if not like drastically different. So I have taken enough points here, enough areas here. Okay. So now what I will do, I will construct a curve for this. I think this is V. Let's so you see that this is our average of all, and all these areas, you see that there is a deviation, and deviation only in one direction. So that means they are over predicting the whatever value we are taking, we are measuring V here. So they all of them are over predicting this. So this is not the RVE, and you have taken this. This is one reference. I'll just minimize this. I'll do one more exercise here. So I'll delete these areas, and I'll take bigger areas, just for the sake of example, I'll draw one area here. Let me put it to our previous location. So when you find the RVE, it should be independent of the location. But because our material is like non-uniformly loaded, so it's dependent on the location also. So I'm taking a bigger area than previous one. And on purpose, I'm taking bigger area just to explain how uh, RVE or the size of the element which we have taken affect the material properties. And one important point is that these areas should be at different locations. If you take different area at the same location, then you will, of course, you will not get any variation. So that will also confuse you. So at as different as possible, you try to take these areas at different locations, as different as you can take. So this time I have taken little bit bigger than the previous time, and once again I will compute the same properties v. So now if you see here, so they are more closer to each other than the previous case. Okay, so if you take the previous case, if I have here, so these are the previous cases here. I have to check the scale here. So this is between uh, somewhere 67 and 59, and this one is 66 and 57, little bit like wider. And this we are measuring v only. If we take the exx or different the other property like strain and all, you will get much better idea on how the size is affecting the properties. And like I said, we cannot call it as RVE. We cannot define RVE in a condition where the loading is non-uniform. So that's a crime to say it as RVE. But for the sake of example, we have considered this as that how do we compute RVE. So you keep on increasing this size, keep on increasing the size of these boxes. The moment you get some convergence, the moment you find that these curves are overlapping with each other, then you can say that, oh, I found my RVE. So once there is some convergence, and convergence means now if you take a bigger size, you will not get any variation further. The point where, and after which, if you increase something and if you don't get any variation, you call that point as convergence point. So if you have converged your properties to an area where you don't get any further variation, you call that area as your RVE. And although we are computing area here, we are still calling it as RVE volume, because we assume that there is no variation in this plane, in the Z plane. We assume, based on that assumption, we are saying this as RVE. And this is not the property of area. We know that this is not the property of area. The thickness which we have taken, the thickness of the sample, we have taken that thickness to be sufficient enough that there is there is no variation. So that thickness is large enough. So based on that, it's a property of area into that thickness which we have taken. So it's a volume. Okay, it look like an area, but it's a volume. Okay, so this is your RVE. Maybe it should be clear, so you can stop.